Imagine you're a developer at a company that builds an AI agent, and your product manager comes to you and says, when the agent encounters a tool failure, I want it to retry 3 times before falling back to asking the user for help. That sounds like a simple ask, but before you can write a single line of code, you need to answer a much harder question. Where in this sprawling code base does the retry logic actually live? Is it in the main loop, the tool executor, split across a parser, a state manager, and an error handler? This is the puzzle that the paper we're looking at today tackles head-on. The authors focus on what they call the agent harness, which is the software scaffolding around a foundation model that constructs prompts, manages state, invokes tools, and coordinates execution. As models improve, APIs shift, and product requirements change, the harness itself has to evolve constantly. And every evolution starts with the same painful step, figuring out where a given behavior is implemented. The authors call this behavior localization, and they argue it's the real bottleneck, not the actual code writing. A production harness might span hundreds of functions across dozens of files, where one behavior touches non-adjacent code sites connected only through shared state. Whether a human or a coding agent is doing the work, they have to build a mental map connecting what the system does to where it does it. Prior work has tried to make code easier to explore in various ways. Repository maps give you structural overviews. Code search lets you find snippets by keyword. Repository memory systems let coding agents cache what they've learned. Long context models let you stuff more code into a single prompt. But all of these approaches share a common blind spot. They organize information around files, functions, and modules the way the code is stored on disk. A modification request, though, describes a behavior, meaning something the running system does. Bridging that gap from behavior to implementation is still left to the developer or agent to figure out on their own. The paper's core contribution is what they call the Harness Handbook, which is essentially a behavior-first table of contents for a code base. Think of it like the difference between a car's parts catalog and its service manual. The parts catalog tells you every component and where it sits in the vehicle. The service manual tells you, if the engine won't start, here are the 5 subsystems to check, and here's how they interact. The handbook is that service manual, automatically generated from the source code. It's organized as a 3-level hierarchy. Level 1 gives a system overview, the architecture, the execution model, the major stages. Level 2 zooms into each execution stage, describing responsibilities, inputs, outputs, and dependencies. Level 3 provides deep dives on individual units of code, each linked back to a specific location in the source. Alongside this hierarchy sits a state register that tracks how shared state flows across stages, which is critical because that's often how behaviors get distributed across seemingly unrelated files. The construction pipeline that builds the handbook has 3 phases. First, a static analysis phase parses the code deterministically, extracting functions, call graphs, and external boundaries with no language model involvement, keeping this foundation grounded and reliable. Second, a behavioral organization phase uses a language model in a propose and review loop to map source units onto execution stages. Depending on whether the codebase has a trustworthy seed skeleton available, the pipeline either uses function-level granularity or falls back to file-level granularity. Third, a synthesis phase weaves everything into the 3-level document tree, ensuring every leaf entry points to a verified source location. The whole thing follows 2 guiding rules. Progressive disclosure means you only descend deeper when the task demands it, keeping cognitive load manageable. Behavior implementation alignment means every source pointer must actually resolve in the current repository, and if it doesn't, that entry gets frozen rather than lying to you. The workflow for using the handbook to make changes is called Behavior-Guided Progressive Disclosure, or BGPD. When a modification request arrives, the coding agent first navigates the handbook from top to bottom, identifying which stages are relevant, then following state relationships to catch stages that are coupled through shared data even if they aren't structurally adjacent. Only then does it drill into level 3 entries and open the actual repository to verify that the candidate locations still make sense. The planner then produces an edit plan with action declarations. An executor applies those changes, and any non-empty diff triggers automatic resynchronization of the handbook, so it stays in lockstep with the code. The resync is careful to update only what changed rather than rebuild from scratch. The experiments evaluate this on two open-source harnesses, Terminus 2 and Codex, with 30 modification requests each. Requests are categorized as query changes, cross-file additions, or search hostile requests, where keyword search would fail. 3 independent language models judge plan quality on localization accuracy, scope control, and reasoning quality. The results are striking. On Codex, the handbook-assisted ARM wins 38.3% of comparisons versus 28.3% for the baseline. On Terminus 2, it's 45.6% versus 26.7%. And this improvement comes with lower token usage, roughly 9 to 30% fewer planner tokens per request. So the handbook isn't just paying for itself with more context, it's actually making the search cheaper. When they compare the weaker planner's outputs against reference plans generated by stronger models like Opus 4.8 and GPT 5.5, all 24 precision recall and F1 metrics improve, with some F1 gains reaching nearly 19 points. Complete localization failures, where the plan has zero overlap with the reference, drop by up to 26 percentage points. Now for the honest caveats. The evaluation uses language models as judges, which introduces the usual concerns about judge bias, though the authors mitigate this by using 3 different judges and requiring a 3-point margin for a declared win. The 2 evaluated harnesses are relatively well-structured open-source projects. And it's an open question how the construction pipeline scales to truly massive, messy enterprise codebases, where the stage skeleton itself might be ambiguous. The resynchronization procedure assumes the code parses cleanly and that fingerprinting can match functions across versions, which could break down under aggressive refactoring. And the file as leaf mode, used when a good seed skeleton isn't available, likely produces a coarser handbook that may not localize behaviors as precisely. Looking forward, the authors hint at what feels like the more interesting horizon, using the handbook as shared behavioral memory for self-evolving agents. Once you have a synchronized behavioral map of your own runtime, an agent can close the loop of localization, planning, execution, and resync autonomously, effectively teaching itself how it works and modifying itself accordingly. Now let's walk through some questions you might have after hearing all of this. You might be wondering, why does organizing knowledge by behavior actually help more than just giving the agent better search tools? The key insight is that behaviors in production systems are almost never localized to one file. They emerge from interactions across stages connected by shared state. Search tools return code that matches keywords, but they can't tell you that a retry policy involves both the tool executor and the state manager, because those 2 components communicate through a scratchpad. The handbook explicitly encodes those cross-stage relationships, so navigation follows the causal structure of the running system rather than the alphabetical structure of the file system. Another question is, if the handbook needs to stay in sync with the code, doesn't the resync overhead eat up all the savings? The authors designed the resync to be incremental and mostly deterministic. Only 4 semantic steps involve language model calls: classification, file assignment, within-stage organization, and description revision. Everything else, like reparsing, updating the call graph, matching functions via fingerprints, is handled by static analysis. And if the underlying stage skeleton is still valid, only the touched entries get refreshed. So the amortized cost per modification is small, especially compared to the cost of a coding agent thrashing through an unfamiliar repository. Finally, you might ask, could you just use a long context model and stuff the whole codebase into the prompt instead? You could try, but long context approaches still leave the agent to figure out the behavior to code mapping on its own, just with more raw material to sift through. The handbook's contribution isn't giving the model access to more code, it's giving the model a pre-computed map of how that code produces behaviors. Even a stronger model with a bigger context window would benefit from starting with a behavior-oriented index rather than a raw dump of source files. Now, how might these ideas apply to large-scale recommendation systems? Consider a ranking pipeline serving hundreds of millions of users, where a request like reduce over-recommendation of clickbait for users under 25 might touch the candidate generator, the feature store, several ranking model heads, a re-ranking business logic layer, and a diversity constraint module. That's exactly the kind of behavior that lives across non-adjacent code sites connected by shared state, whether that state is user embeddings, session context, or feature vectors. A handbook-style representation could give ML engineers and internal coding agents a behavior-centric map of the recommendation harness, letting them find every site that influences a given behavior before proposing changes. More practically, the state register concept maps beautifully onto the flow of features and embeddings through a recommender. You could imagine a handbook that tracks how a user's watch history flows from the ingestion service into candidate retrieval, gets transformed by feature crosses, feeds into multiple model heads, and eventually shapes the final ranking. When an experiment shows an unexpected regression, engineers could use behavior-guided progressive disclosure to trace the affected stages rather than grep searching through millions of lines of production code. And for teams increasingly relying on coding agents to prototype ranking changes or write feature engineering logic, having a synchronized behavioral memory could dramatically reduce the wall time between "we noticed a bad pattern" and "we have a targeted, well-scoped fix ready for A/B testing."